Rahim. In this video we will discuss the 1x4 demultiplexer MUX or MUX implementation into the Verilog HDL using the different methods. Here is a simple circuit diagram of the DE-MUX which have one input and four outputs here, and these are the two selective pins from which we select the 0, 1, 0, 0, 1, 0, 0, 1 and 1, 1. Input remains 1, D in remain 1, and here we change. When the A1 and A0 here the at selective pin, when the input is 0, 0, then it passes through the NOT gates. A0 pass through this and goes to here, and from this it passes to the NOT gate and go to here, and D in shows output at Y0. Similarly, when we have 1, 1 here, so it when it passes to the NOT gate it becomes 0, and so it will pass through this simple wire and goes to the Y3. And when it has the 1, 0 value or 0, 1, it at 1, 0 value it goes to the this wire and go to the here, and it shows the value at Y2, and when the value is 0, 1, it shows the output D in is equal to Y1. Now we go to the methods. Here is a truth table. When the D in is 1 at all the four stages, and when it shows 0, 0, the output is 1 is equal to at 0 Y0. When it is 0, 1, it is it show output at Y1. When it is 1, 0, it show output at Y2, and when it is equal to 1, 1, it show output at Y3. If we convert the A1 and A2 into the unsigned decimal, we can also say that when the selective input is 1, it show the output at Y0. When it is the selective input is 0, then the output is at D in is equal to Y0. When the input is A1 and A2, input is 1, the D in is equal to Y1. Similarly, when 2, D in is equal to Y2, and when it is equal to 3, D in is equal to Y3. Here is the first method using the gate level implementation. We write the code of the gate level implementation. Here is the module and file name 1 to 4. We don't declare here the variables. We directly define the input and output with the variables by using the brackets here, and declare direct input and output here. Here we declare the input and output, and here we define the NOT gate, which is equal to A1, A0, A1n is equal to here this wire is A1n and this wire is A0n, and here is the A1 and A0. That's are the NOT pins, and here he defined the AND and all the AND gates. Now we simply copy this and test this into the quarters. Here we have to simply copy this and go to the here. We select the Verilog HDL file here and paste the program here. We have to change the name of the file here, which is DM1. Here we declare the variables, and here NOT gate and AND gate, and here we end the module. gate level implementation. Now we run this simulation here to study their behavior. It takes some time to simulate. Now we can see here the full compilation was successful here, and now we can check the verify the RTL view here. Here is RTL view of this. It is the condition of 1 1, and here is a 0 1, here is 1 0, and here is a 0 0. Now we go to the waveform. University program EWF. Here we insert the node, list it here, copy this, and OK. Now here is we set the value of A1 and A2, and we can find the output at Y. We can set this 1 and at 0 0. You can see this. What is the output at 0 0? The simulation is running. Here we have to set the D in is equal to 1. Here all is equal to 0. V1 is equal to 1. Now we run the simulation again. Here we can see that when the both are the 0, then it shows the output at Y0, as shown in here. When the A1 and A both are the 0, here they both use the at both cases NOT gate. When both are the 0, it shows the output at Y0. Now we go to this and we set this 1 and simulate this again. Now we can see this again. When A0 is equal to 1 and A1 is equal to 0, it shows the output at Y1, as we can relate it from circuit diagram. When it is equal to 1 0, here is a 1 0, and output is shown in Y1. Now we set the A0 is equal to 1 and A1 is also 1. Now we simulate this again. Now here we can see that when both A0 and A1 is equal to 1 1, it shows the output at Y3, as in RTL view circuit diagram. When both are the 1 1, it shows the input at Y3. That's all for this method. Now we go to the next. And now here is a case using the case statement. Here we simply define the module, and as above, here we direct declare the outputs and input and their bit size here, and we use the always command to continuously updating the Y and A value. Here we take the y as output and input is equal to a. D in is equal y is equal to 4 bit, y is equal to d is 4. We collect this into the 4 bits, and a is equal to 2 bit number, which is equal to a1, which is the sum of a1 and a0, and d is same as given here. Here is a now y is output and a is equal to control, selective control. And here is a case study begins, and here we define the cases. When the case is equal to 0 0, it shows the y0, it shows the d in is equal to y0, input shown on y0. Similarly, when it is 0 1, it shows the input at y1. When it is equal to 1 0, it shows the input at y2. When the both are the 1 1, it shows the input at y3. Now we copy this and check this also on the Quartus. Here we copy this and go to the Verilog HDL file. Here we simply paste it here. Here is a 4 cases I explained below. At 0 0, y0 is equal to d in. At 0 1, it shows the input at y1. At 1 0, it shows the input at y2. At 1 1, it shows the input at y3. And at y0, y is equal to 1 to 3 bit. Here we define the bits, and here and the cases. Here we have to change the name of the file, which is equal to dm2. Here we define declare the inputs and output directly. Now we run the study. It takes some time to simulate. Here we can see the full compilation was successful. Now we write here case using case implementation. Now we can relate the RTL view by locating in RTL viewer. Here is the RTL view of the 1 to 4 mux. Here is a 1 bit and y is equal to 4 bit number. Here is a d in is 1 bit and a is equal to 2 bit number. That's the circuit diagram of this. Now we go to the waveform, University program VWF, and we insert the node here. Here we node finder list, copy this and click on OK. Here is the we can see the y is equal to 4 bit output and a is equal to selective pins are the 2 bit and d in is remains 1, which is equal to 1 bit. When it is equal to 0 0, we simulate this and check this. Now we can see here when the input is equal to d in is equal to 1, it remains always 1. When the selective control pins is 0 0, a1 and a0 is equal to 0 0. it shows the 1 at the y1. It shows the input at y0 because the last bit is equal to 1. It shows the output at y0. Similarly, when we define it, we set that it is 1 1. Now we simulate this again. Here we can see this. When the both are this 1 1, it shows the 1 at the y3. Similarly, when it is equal to 1 0, it shows the at y2, and when it is equal to 0 1, it shows the output at y1. No, that's all for this. We go to the next case here, using logic state here statement. Here is a code for by using the logic statement. Here we simply define the module and input output as above. We directly declare the input and output by using the bracket here, and here we assign, and by using the logic statement declare here the main body of the code, and here we end the module. Now here we assign when when DE is equal to at y0, then it passes through the both a0 and a1 passes through the NOT gate. It is the symbol of the NOT gate. And when input is equal to y1, then it is equal to a1 pass through the NOT gate, and a0 can directly through the wire. And similarly here at y2, a1 pass through directly from wire, and a0 from the NOT gate, as shown in the above. A1 pass through the NOT gate, and a0 directly from this wire. When it is equal to 1 1, it directly pass through both lines are passed through directly the wire. Then the NOT gate are not be used. Here is the logic. Now we copy this and test this into the software. Copy this. Now we go to the repositories. Here we go to the Verilog HDL file, and okay, we paste it here, and we write it here using we use here the logic statement. Using logic statement. I explain the code again. Here we define the module, and here we have to change the name of the file, which is equal to dm3, and here we directly declare the output, which is equal to 4-bit output is equal to y, and input is equal to 2-bit a, and the second input is equal to d, which is 1-bit input. And here we assign when d is equal to y0, the both are passes through from the NOT gate, and when the d is equal to y1, a1 passes through the NOT gate, and a0 passes through directly from the wire. And when d is equal to y2, then a1 is equal to directly from the wire, and a0 from the NOT gate, through the NOT gate. And when it is equal to y3, then both directly pass through the wires and not from the gates. I write it here. The condition is 0 0. Here is equal to 0 0. here is equal to 1 0, 0 1, here is equal to 1 0, and it is equal to 1 1. Now we run the simulation. It takes some time to simulate. Here we can see that the full compilation was successful, and now we go to the relate the RTL view by locating in the RTL viewer. Here is the RTL view of the this MUX DE-MUX, and now we go to the university program VWF. Here is the we insert the node here. Here is the node finder, list it here and paste it. Okay. Here D in remains 1. We set it D in is equal to 1, and A is equal to, when A is equal to 0 1, we test there is a 4 total cases. We test the any one of 2 from them. Let we take the 0 1, and it gives the input from at y1. We set this. We can see here it shows the input at y1 second bit. It shows the D in is equal to y1 when it is equal to 0 1. Now we set this both 1 1. When both A1 and A0 are the 1 1, it shows the output at y3. Now we simulate this again. Here is the, we can see this, it shows the output at y3. D in is equal to y3 when both A1 and A0 are the 1 1. Now this case is also verified. Now we go to the next case using the conditional statement. Here is the fifth case using the conditional statement. In this it used the if else statement. Here is a module, and here declare the variables. Here it simply declare the wires input and output. Here it use the always to update, continuously updating the input, and the here it use the D in as output and SEL as the as above. We use the A1 and A1 and A0, and D out is equal to Y in the circuit given. So it define this. Here it is if use the if and else statement. If the selective pins is equal to 0, we named this as a selective pin. If the selective pin is equal to 0, then D out is equal to D out is equal to D in at third bit. At third bit. Else if if is equal to 1, then it shows D out is equal to at second bit. Then similarly else if selective pin is equal to 2, 2 means 1 0, then the selective D out is equal to at y1 means it is at the D0 y0 y1, else it is at the y0. Now we simply copy this to test the study. We can also modify edit it according to our name. we go to the corpus. Now we copy this and go to the Verilog HDL file here and paste it here. Here we can write using conditional statement. Here we define the output input and the model name here, and here we use the always to continuously refreshing the in and the setting pins. Here it is if they as if we change this as A, we named it A, which have the two inputs D out, and this is name this A. If A is equal to 0, then the D out is equal to D in, and if else if A is equal to 1, then D out is equal to at second bit. If A is equal to 2, then it is equal to at third bit, and if else it is equal it at the last bit, fourth bit. Now we run the study. We have to change the name of the file here, which is equal to DM5. Here is the fifth method. Here it shows some error. We have to reset this all value. Here we change the file name, we set it back, and we change the file name DM5. Now we run this. This time it again show error. The error is here. Here is missing something, this colon. Now we see the another error. If else and there is no seam there. Now we run this again. It has shown. Here we end the module, and now we run this again. Now he is running. The mistake is here we don't mention the end the module. Now we can see here the full compilation was successful, and we can see the RTL view from locating this. Here is a DE-MUX 1 grosh 4 DE-MUX. Here is a D in 1 bit and D out 4 bit, and here is a setting pins 1 bit, and we use the logical equality in the code with these are the symbol of the logical equalities. Now we go to the university program VWF and insert the node here, node finder, and here we list it, copy this, and okay. Here we set the D in is equal to 1, and D out is the output, and we set the pins at 1 0. Here is our total 4 cases, which is 0 0 1 0 0 1 and 1 1. We will check this by 2 and verify this. Now we run the study. Now we can see here it show in the output when it is equal to 1 0, it shows the output at second last bit, second bit. It is equal to D out second bit. When it is equal to 0 0, it shows the output at first bit, and when it is equal to 0 1, it shows the output at second bit. When it is equal to 1 1, we set this 1 1, and then it shows the output at 1 0 0 0 0 at the fourth bit. Now we run the simulation and check this. Here we can see this. When both are the 0 0, it shows the output at the last bit, fourth bit. It in the previous we can remember this as y0, y1, y2 and y3. And from the circuit diagram we can set this. In this case we will study this as when both are the 1 1, it shows the output 1 at the fourth bit. Now that's all for this. This got verified, and now we go to the next stage. Now the next one is sixth is using a sign statement. Here is we simply declare this and directly declare this output and input in front of the module name, and here we assign directly using the assign statement as above. Case as above. When the DIN is equal to y0, it shows it is equal to 0 0. In this case, when DIN is equal to y1, it is equal to 1 0, and similarly 0 1. And when it is equal to DIN is equal to y2, at DIN input is equal to at y2, it is 1 0, and at 1 1 it shows the input at y3. We simply copy this and run this in it. Now we go to the quarters. Here we go to the Verilog HDL file here and click on OK. We simply paste it here. Here is a using assign statement. Here we simply declare the variables input and output. Here we use by using assign statement. We declare this. I explain this, and now we run the simulation. It shows some error because we have to change the file name here, which is equal to DE-MUX. Now we run the simulation. We can see this, the full compilation was successful, and we can see this by locating the RTL view here. Here is the RTL view of this. Now we go to the uniform program VWF. Here we insert the node, list it here and copy this. OK and OK. Here is a 2-bit number which is equal to, we set this 1 0, and DIN is equal to always 1, and y is equal to 4-bit number. Now we simulate this. It shows the output at y2, because 0 is equal to 2. So if it is equal to 0 1, then it shows the output at y1. Now the simulation is running. Here we can see that it shows the output at y2 at second bit. Now when it is we set this at 0 1, and it shows the then it shows the output at y1, and when the both bits are the 0 0, we set this is 0 0, and both are the 0 0, then in simulate this, it shows the output at y0. We can see this after the simulation. Here is a generating simulation. Now here we can see that it shows the output at y0. y0 is equal to d in when both are the 0 0, and when both are the 1 1, we set this 1 1, then it shows the now it shows the output at y3 is equal to d in. Now we can see this from here. It show output at y3 is equal to d in when both are the 1 1. That's all for so this method is verified. Now we go to the next method here, which is equal to using block always block. Here is the using always block code. We use here always at the rate of by registering register output. It is used to continuously refreshing or updating the y and a output and input according to the given condition. It is so relatable to the case study. We have defined it by copying this, and we also declare it in the previous here. In using case statement, we use always here also in case study. So that's all for the that are the 7 methods to define the Verilog code of the 1 to 4 multiplexer or MUX implementation. That is the basic diagram of the. That's all for